This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we'll be delving into a research paper titled LM plus AL, Bridging Large Language Models and Action Languages for Complex Reasoning About Actions. This paper proposes a novel method to enhance the complex reasoning capabilities of large language models, LLMs. Let's start with the core problem the authors addressed. What are the limitations of LLMs when it comes to complex action reasoning?
Current LLMs, while impressive in many natural language tasks, often falter when faced with complex action reasoning problems requiring systematic search. They struggle to generate effective plans, especially when dealing with intricate constraints or scenarios requiring adaptation to novel situations. The problem isn't just about finding a solution, it's about consistently finding correct solutions, even with minor variations in the problem description.
The paper suggests bridging the gap between LLM's strengths in natural language understanding and the formal reasoning capabilities of action languages. Can you elaborate on the rationale behind this hybrid approach? Why not rely solely on LLMs or solely on action languages?
Using LLMs alone often leads to inconsistent results and a lack of robustness in complex scenarios. Action languages, on the other hand, offer formal semantics and efficient reasoning tools, but lack the natural language understanding capabilities of LLMs. The LLM plus AL approach leverages the strengths of both. LLMs handle the semantic parsing and knowledge extraction from natural language problem descriptions, while action languages provide the formal framework for systematic reasoning and plan generation.
The paper mentions using the action language BC+. What are the advantages of BC+ compared to other formalisms like PDDL, which have also been explored in conjunction with LLMs?
While PDDL is a widely used standard for task planning, BC Plus offers greater expressivity for representing more general forms of knowledge about actions. This includes state constraints, indirect effects, default reasoning, and recursive definitions aspects often crucial for complex reasoning problems. BC Plus's intuitive natural language like syntax also makes it more amenable to LLM-based generation.
The LLM plus AL pipeline involves several stages. Can you walk us through the process, highlighting the role of the LLM in each stage?
The pipeline begins with BC Plus signature generation, where the LLM extracts relevant symbols and types from the problem description. Next, the LLM generates common sense and domain-specific knowledge statements in natural language. This knowledge is then translated into BC Plus rules by the LLM, guided by a prompt detailing BC Plus syntax and semantics. Finally, a self-revision stage iteratively refines the BC Plus program based on feedback from the BC Plus reasoner.
The self-revision stage is particularly interesting. How does this iterative refinement process improve the accuracy and robustness of the generated BC Plus programs?
The self-revision stage uses the BC Plus reasoner to check for satisfiability and consistency. The LLM generates sample queries to test the program's behavior. Based on the reasoner's output and the results of these queries, the LLM revises the BC Plus program, addressing both syntactic and semantic errors. This iterative process significantly improves the quality of the final BC Plus program, often reducing the need for extensive manual corrections.
The paper evaluates LLM plus AL against several state-of-the-art LLMs on benchmarks involving variations of the missionaries and cannibals puzzle. What were the key findings of this comparative analysis?
The results showed that standalone LLMs, even with human feedback, struggled significantly with the benchmark problems. LLM plus AL, however, consistently produced correct solutions with relatively minimal human corrections. This highlights the limitations of LLMs in systematic reasoning and the benefits of integrating them with a formal reasoning framework like BC+.
The paper also compares LLM plus AL with using LLMs to generate Python code for solving these problems. What were the relative strengths and weaknesses of these two approaches?
The LLM plus code approach, while capable of solving some problems, struggled with adapting to problem elaborations. The LLMs often failed to accurately model actions or constraints, and the generated Python code was often difficult for humans to correct. LLM plus AL, on the other hand, benefited from the declarative nature of BC+, making it easier to identify and correct errors. The BC Plus reasoner also handles the search process efficiently, unlike the often inefficient search algorithms generated by LLMs for Python code.
The paper emphasizes the importance of elaboration tolerance, the ability of an AI system to adapt to new information or altered circumstances. How does LLM plus AL demonstrate superior elaboration tolerance compared to the baseline LLMs?
The benchmark problems included several elaborations of the missionaries and cannibals puzzle, introducing variations in constraints and initial conditions. Baseline LLMs frequently violated constraints or failed to adapt their solutions to the changes. LLM plus L, however, demonstrated a much higher degree of robustness, consistently producing correct solutions even with these elaborations, often requiring only minor adjustments.
What are the key limitations of the LM plus AL approach, and what are potential avenues for future research?
While LLM plus AL significantly improves upon standalone LLMs, it still occasionally requires human corrections due to errors in LLM-generated BC plus code. Future research could focus on improving the LLM's ability to generate correct BC plus code through techniques like fine-tuning or more sophisticated prompting strategies. Exploring other action languages or integrating more advanced reasoning techniques could also enhance the system's capabilities.
The paper highlights the challenges LLMs face in consistently adhering to state constraints. Can you elaborate on the nature of these challenges and how LM plus AL addresses them?
LLMs often struggle to maintain consistency across multiple steps in a plan, leading to violations of state constraints. They may generate intermediate states that violate constraints, but fail to recognize or correct these errors. LLM plus AL mitigates this by leveraging the formal semantics of BC+, which enforces constraints during the reasoning process. The self-revision stage also helps identify and correct constraint violations through the feedbacks from the BC+ reasoner.
The discussion of solvable versus unsolvable problems is also interesting. How does LLM plus AL handle the distinction compared to the baseline LLMs?
Baseline LLMs often hallucinate solutions for unsolvable problems or incorrectly identify solvable problems as unsolvable. LLM plus AL, by using the BC+ reasoner, can reliably determine the solvability of problems within a specified search depth. While it doesn't guarantee finding solutions of arbitrary length, it provides a more robust assessment of solvability than the baseline LLMs.
The paper mentions that the declarative semantics of BC Plus is a key advantage. Can you explain why this is the case?
The declarative nature of BC Plus allows the LLM to focus on specifying what needs to be achieved rather than how to achieve it. This contrasts with the procedural nature of Python code, where the LLM must explicitly specify the algorithm and its implementation details. The declarative approach simplifies the LLM's task and makes the generated code easier to understand and correct.
The success of the self-revision mechanism is noteworthy. What are the key factors contributing to its effectiveness?
The effectiveness of self-revision stems from the combination of LLM capabilities and the formal feedback from the BC Plus reasoner. The LLM's ability to generate and interpret natural language, combined with the reasoner's ability to detect inconsistencies and provide precise feedback, creates a powerful, iterative refinement loop. This allows the system to learn from its mistakes and progressively improve the quality of the generated BC Plus programs.
The paper mentions that LLM plus AL benefits from human corrections, unlike the baseline LLMs or the LLM plus code approach. Can you elaborate on this difference?
While LLM plus AL still requires occasional human intervention, the errors are typically relatively minor and straightforward to correct due to the clarity of the BC Plus representation. In contrast, the baseline LLMs showed little improvement even with extensive human feedback. The LLM plus code approach generated complex Python code that was significantly harder for humans to understand and correct.
The paper concludes by suggesting avenues for future research. What are some of the most promising directions for extending and improving the LLM plus AL framework?
One promising direction is to improve the LLM's ability to generate correct BC Plus code through fine-tuning or more advanced prompting techniques. Another is to explore the integration of more sophisticated reasoning techniques or different action languages. Investigating the scalability of LLM plus AL to larger and more complex problems is also crucial.
The paper's analysis of program issues provides valuable insights into the types of errors LLMs make when generating action language representations. Can you summarize the main categories of errors identified?
The main categories of errors were signature issues, missing declarations, syntactic or semantic errors, rule issues, missing necessary rules, harmful rules or incorrectly implemented rules, and query issues, syntactic or semantic errors. These errors highlight the challenges LLMs face in understanding and correctly representing complex logical relationships and constraints.
The use of the missionaries and cannibals puzzle as a benchmark is interesting. What makes this puzzle a suitable testbed for evaluating complex reasoning capabilities?
The Missionaries and Cannibals puzzle and its elaborations are well suited for evaluating complex reasoning because they require systematic search, constraint satisfaction, and the ability to reason about the consequences of actions. The elaborations introduce variations that test the AI's ability to adapt to new information and handle unexpected situations, making it a robust benchmark for assessing elaboration tolerance.
Paper highlights the challenges LLMs face in distinguishing between solvable and unsolvable problems. How does LLM plus AL address this challenge?
Baseline LLMs often fail to reliably distinguish between solvable and unsolvable problems, either hallucinating solutions for unsolvable instances or incorrectly classifying solvable problems as unsolvable. LLM plus AL leverages the formal semantics of BC plus to provide a more robust assessment of solvability, although it's limited by the search depth it can explore.
The paper emphasizes the importance of the declarative semantics of BC Plus in simplifying the LLM's task and making the generated code easier to understand and correct. Can I elaborate on this point?
The declarative nature of BC Plus allows the LLM to focus on describing the relationships between actions and their effects without needing to specify the exact algorithm for finding a solution. This contrasts with the procedural approach of generating Python code, where the LLM must explicitly define the search algorithm and its implementation details. The declarative approach simplifies the LLM's task and makes the resulting code more human-readable and easier to debug.
This has been a very insightful discussion on the LLM plus AL framework and its implications for advancing complex reasoning in AI. Thank you.